Hello. In this video, we'll be discussing some basics about permutation groups, and specifically about the cycle notation that's used when discussing elements of permutation groups. I will be assuming some basic knowledge of group theory by the listener. So, let's start off with the goal of permutation groups. The goal of permutation groups is that we wish to rearrange n distinct objects. As an example, consider the following. Suppose that we have three objects, which I will label A, B, and C. And there'll be these dots here. Suppose we wish to find all of the possible ways of rearranging these dots, which I've labeled A, B, and C. Since this is such a small group, I can actually write out an exhaustive list of the elements. They are the following. Well, to start, we can have what we have already, so A, B, C. We can also swap B and C, so we could have A, C, B. Next, we could have B on top, so we could have B, C, A, or we could have B, A, C. And finally, we could have C on top, so we could have C, A, B, or we could have C, B, A. And this is an exhaustive list of all of the elements. So notice here that there are 6 elements. This group is called the permutation group of 3 elements. So it's often labeled Sn or sigma n by some people. I'll be calling it Sn. So Sn is called the group of permutations of n distinct things. And as a note, Sn has n factorial elements. So here we're considering, this is an example of S3. So there should be 3 factorial elements, and that's exactly what we have, because 3 factorial is 6. So we've already seen an example of the group of permutations. And this is in fact a group, because each permutation has an inverse. You can consider there to be some identity element. Say, for example, it's ABC. So the identity keeps A at A, keeps B at B, and keeps C at C. One such element could just be a swap of the bottom two, or a swap of these two. And of course, there are inverses of all of these actions, so this does in fact form a group. And the group action is associative. But I'm not going to be discussing the details of why this is a group. I'll just leave it up to intuition to say that it is a group. So now let's look at some of the notation used when discussing elements of the permutation group. So suppose we have an ordered set, which I will call A, B, C, D, E, F. So we have 6 elements here. And furthermore, we have some permutation, which I will call theta. So theta is a permutation which sends these 6 objects in this order to the following. It sends it to B, E, F, A, D, C. Well, we can represent this as the following. We can just say theta is a map which maps A, B, C, D, E, F to the ordered set B, E, F, A, D, C. Or we could say that theta is equal to the following. It's equal to 2, 5, 6, 1, 4, 3. And another way of writing this notation is the following. So we have 1, 2, 2, 5, 3, 6, 4, 1, 5, 4, and 6, 3. So this is one way of writing out permutations, or elements of Sn. Here it would be S6. And the way to read this is the following. So the two-line notation is a little bit easier, just to start with, and you read it as follows. So the bottom line details the old location of the ordered set, and the top line here reads out the new location. And because the top line is inherent in the position of the bottom line, we can often just forego writing the top line at all. What I mean by that is, for the one-line notation on the left here, we already see that 2 is the first element, and 5 is the second element. 6 is the third, 1 is the fourth, 4 is the fifth element, and 3 is the sixth. So you can already see the top line without having to actually write it. Some people write it just to be explicit, but oftentimes one-line notation is used instead because it's easier. You don't have to write a whole nother line of numbers. But what this means is the following. So we consider the set A, B, C, D, E, F. Then, if we act on it with theta, we do the following. We say, well, the old location is 2. So what is at the old location in A, B, C, D, E, F? It's B. So B is 2 here, and it's what the first element here acts on. And the new location is 1 because 2 is in the first position. So we say that the second element maps to the first element. So we say that B goes to the first position. Then the old location next is 5. So 5, what is the fifth element here? The fifth element is E. So we say that 5 goes to the second position. So E goes to the second position. 6 is the old position, which is F here, and that goes to the third position. So F is the third position. Next, 1 is the old location, so that's A, and that's mapped to the fourth position because that's the fourth element from the left. So A is the next one. Next, we have 4 is the old position, so that's D, and since that's the fifth element here, D gets mapped to the fifth element. And finally, we consider 3 as the old location, which is C, and that gets mapped to the sixth position. So C goes to the end. And that's exactly what we have up here. So that's how you would read this one-line or this two-line notation. Next, let's consider the combination of two permutations. So suppose now we have another permutation, psi, which is equal to, in one-line notation, 4, 5, 3, 6, 2, 1. Then we say that psi composed with theta acting on A, B, C, D, E, F, well, that's equal to 4, 5, 3, 6, 2, 1, composed with theta, which is 2, 5, 6, 1, 4, 3, and that's acting on A, B, C, D, E, F. Then we already found what theta times A, B, C, D, E, F is. So we can just write psi, which is 4, 5, 3, 6, 2, 1, acting on B, E, F, A, D, C. Then we write the following. We say that the old position is 4, and that gets mapped to the first position here. So whatever the fourth element of this is, that's now the first element here. So the fourth element here is A. So A gets mapped here to the first position. Next is the fifth element of this, and the fifth element is D. So we have AD, and then the third element is F, the sixth element is C, the second element is E, so that goes in the fifth position. And finally, we have the first element here goes in the last position. So we have B at the very end. So the answer should be ADFCEB. Or, writing this out, we say this is something, some permutation, acting on the original ABCDEF. So what we're trying to do is we're trying to write a single permutation, which is actually the combination or the product of these two combinations. Well, just looking at it, we see that the first position here is A, and the first position of the argument is A. So 1 goes at the start. Next, we have D, and that's the fourth position here. So next is 4, and then we have F. F is at the very end, so it's 6 is next. And then C is next, and C is the third position of the argument. So we have 3, and then E. E is the fifth position of the argument, so that's 5. And at the very end, we have B. B is the second element of the argument, so it becomes 2. So 1, 4, 6, 3, 5, 2, this thing here is equal to psi composed with theta. And the way that you can do this without having to act on some element A, B, C, D, E, F is the following. So what we've found is that theta, psi, which is 4, 5, 3, 6, 2, 1, times 2, 5, 6, 1, 4, 3 is equal to 1, 4, 6, 3, 5, 2. So we know that's what it has to be. And the way that you see this is the following. We say we start with the left. So the first position here is 4. So we draw some arrow from 4 here all the way to the fourth position of the right element. So that's a 1. So that means in the first position here is a 1. Next, we say, well, we have a 5 here, so we go all the way to the fifth position. So because this is a 5 here, and it's in the second position here, and it points to 4, 4 is in the second position. Next, we have a 3. 3 here points to going to the third element. That points to 6. So the third element here is 6. Next, we have in the fourth position a 6. So this thing maps all the way to the sixth element, which is 3. So 3 is next. Then we have a 2 here, so we map to the second element of the right term, which is 5. So 5 is next. And then at the very end, we have a 1. And this maps to the first element, which is 2. So since 1 is in the last position here, and it maps to 2, we see that 2 is at the very end. So the product of these two should be 146352, which is exactly what we found above. So this is one way of multiplying two elements of the permutation group together. As you might notice, though, this is somewhat tedious, and you have to write out all of the terms. Even if one of them is kept in the same position, like here, A is kept in the same position, but you have to write out A, you have to write out 1 in the first position and write out all the other elements. And multiplication is also a little bit tedious. For larger groups and for more elements in your permutation group, this can get very complicated and tedious. So instead, we move on to cycle notation. So instead, we consider cycle notation. So cycle notation begins with the following observation. For theta, which I'll write out again, theta is given by this permutation here. So theta is the following. It's equal to 256,143. And what we notice is that A, so what was A becomes B. And that's because of the one-line notation. We say that the second element of recall that this acts on A, B, C, D, E, F. So what was A in the first position becomes B, and that's because this is a 2 here, and the second position is B. Then what was B now becomes E, and that's because in the second position here, which is what B was, maps to 5, which is the fifth position, or E. Now, what was E now becomes D, and that's because in the fifth position, because we had a 5 here, so we now go to the fifth position, which is a 4. So what was E in the fifth position now becomes 4, which is D, because D is in the fourth position. And then, if we go to the fourth position here, that's a 1. So what was D in the fourth position now becomes what's in the first position, which is A. So we're left with a cycle. So we go from A to B, B goes to E goes to D, and D goes back to A. So since this is a cycle, we can represent this cycle as the following. We can represent it as 1, 2, 5, 4, meaning that the second element goes to the first element. So 2 goes to 1. And the fifth element goes to the second element. That is 5 goes to 2. Then the fourth element goes to the fifth element, because 4 is to the right of 5. And finally, the first element maps to the fourth element. And that's because there's an error. The 1 is on the left here, and it moves to the left, which is all the way back over here, and that's 4. So this is a cycle going around. So that's exactly what we had before. So if we have, let's say, 1, 2, 5, 4 acting on A, B, C, D, E, F, it becomes the following. Well, let's just look at how this is defined above. We say that the first element goes to the fourth element. So in the fourth position here, we should have A. Then the fourth element, which is D, goes to the fifth position. So that means D should be here. Then the fifth element, which is E, that goes to the second position. So E is here. And then the second element, which is B, goes to the first element. So B is in the first element here. And then everything else is left the same. So we have C and F. So this is how 1, 2, 5, 4 would act on A, B, C, D, E, F. And as a note, because this is cyclic, we have that 5, 4, 1, 2 is the same thing as 1, 2, 5, 4, which is the same thing as 2, 5, 4, 1. And this process can go on. So all I'm doing is I'm shifting these elements to the left. So I'm taking 2 and I'm moving it to 1. I'm taking 5 and I'm moving it to 2. I'm taking 4 and I'm moving it to 5. And I'm taking 1 and I'm moving it to 4. When I do that, I get this element. And if I do that again, so I shift 5 to the left, 4 to the left, 1 to the left, and I take 2 and put it to the end, that's exactly what this element here is. And since they all represent a cycle, these permutations are all the same. And moreover, if we look at how theta acts on A, B, C, D, E, F, so if we go back up and look at how theta acts, we said that theta, if you look, it sends C to the sixth position, and it sends F to the third position. So it swaps the sixth position and the third position. So this is also a cycle, because the third position goes to the sixth position, and the sixth position goes to the third position. So this can be represented as 3, 6, because, again, 6 goes to 3, and 3 goes to 6. So theta in total can be written as 1, 2, 5, 4 times 3, 6. And you can also rearrange the order of this, so it could be 3, 6 times 1, 2, 5, 4, and that doesn't matter. So positions that are unaltered by a permutation are either left out entirely from the notation here, or they're written in their own pair of parentheses. So let's say we had a permutation which sent 1 to the first position. Then in that permutation in cycle notation, you would have something that looks like this. So 1 gets sent to 1. Therefore, the identity here, I, is equal to 1, 2, 3, 4, 5, 6. But it's often just written as 1, just for convenience. And the order of the permutation here, so if we considered now orders of the permutation, this simply means given a permutation, let's call it sigma. So given a permutation sigma, so this is some element of the permutation group of n elements. Let's say sigma has order m. Then that means you would have to take sigma to the m, or multiply sigma by itself m times in order to get the identity. So here, looking at cycle notation, in cycle notation, the order is equal to the least common multiple, or the LCM, of the lengths of the cycles. So here for theta, theta has order 4. And that's because we have one cycle of length 4 and one cycle of length 2. And the least common multiple of 2 and 4 is 4. Next, let's consider how we multiply two different permutations and cycle notation together. The way to do this is as follows. So let's consider psi as we had above. So before, psi was equal to 453,621. So psi is equal to 453,621. Or in cycle notation, we see that it becomes, 3 is in the third position. So that means 3 is mapped to itself. Then we see that 5 is in the second position and 2 is in the fifth position. So we have a 2 and a 5, and that's because we have 5 in the 2 position and 2 in the 5 position. Then the remaining elements form their own cycle. So that cycle is 1, 4, 6. So 1 is in the 6th position, 6 is in the 4th position, and 4 is in the 1 position. And that itself forms a cycle. So this is psi in cycle notation. And suppose now we wish to find psi composed with theta. Well, this is equal to 3 times 1, 4, 6 times 2, 5. So that's psi. And we wish to compose this with theta, which we said above was 1, 2, 5, 4, 3, 6. And we wish to act this on A, B, C, D, E, F. Then this becomes, we know how theta acts on it. So we write again psi. So it's 3, 1, 4, 6, 2, 5 times B, E, F, A, D, C. Then we see that the third position remains where it is already. So in the third position, we should have F. Then we say that 5, the thing in the fifth position, goes to the second position. So in the second position, we should have D, because before in the fifth position was D. Then what's in the second position gets mapped to the fifth position. So E here is in the second position, so it should now be in the fifth position. So this is the first, second, third, fourth. The fifth position should be E. Then we have 1, 4, 6. So in the first position, whatever's in the first position gets mapped to the sixth position. So here, B is in the first position, so it's now in the sixth position. Then what's in the sixth position gets mapped to the fourth position. So C is in the sixth position, so it's now in the fourth. So C is here. And then finally, what's in the fourth position gets mapped to the first position. So in the fourth, we have A, so that gets mapped to the first position. So we have ADF, CEB. And that's exactly what we had before. But writing this in cycle notation, we see that we have 1. So A is left in the A position. So we have 1 by itself. So because we're acting on A, B, C, D, E, F, and A is still in the first position, we leave the first element alone. So we just have a 1 here. And since E is in the fifth position here in the argument, and E is also in the fifth position here, we have that the fifth element is also left alone. Then what we find is that the second element, B, so here B is the second element, that gets mapped to the 6th position here. And then the 6th element, which is F here, that gets mapped to the 3rd position. So 6 maps to 3. And then the 3rd element here, which is C, that gets mapped to the 4th position. So then this gets mapped to 4. And then finally, the 4th element here, which is D, gets mapped to the 2nd element here. So we go back to 2, and this forms the full cycle. And the way that you read this, so you know how to write it down in the correct order, is you read it backwards. So you say 4, 3, 6, 2 is the permutation, or in cycle notation. So we have 4, 3, 6, 2. So you read it backwards from the first non-repeated element. And that gives you the full cycle notation of psi composed with theta. So how do we know that 3 times 146 times 2, 5 composed with 1, 2, 5, 4 times 3, 6, how do we know that that's equal to 1, 5, 4, 3, 6, 2? Well, we could, like we just did above, act it on some arbitrary element and then see where all of the elements get mapped to. So where do A, B, C, D, E, F get mapped to? But for larger systems, that becomes somewhat tedious. So the way that you do it is as follows. You go through multiple passes, reading from right to left of the left-hand side. So let's suppose we wish to know what happens to the first element. So the first component of any element that we act on. Well, in the first pass of the left-hand side here, we look for 1. So we see a 1 here. So we have a 1 here, and 1 gets mapped to 4. So we just write 1 gets mapped to 4. Great. Then we move on to the left composition. So here we look for 4. 4 gets mapped to 1. So we write 4 goes to 1. But this forms a full cycle. We go from 1 to 4 and then from 4 to 1. So the way that this is interpreted is you have a 1 here, and in the first pass, so this is pass 1, in the very first pass, you have a closed loop of 1. So since this loop closes, because these two numbers are the same, we say that psi composed with theta has this element, this cycle. So just the 1 cycle. So we leave 1 alone. Great. Next, we consider 2. So in pass 1, let me copy and paste this to move down, just so we can see it. So we have psi composed with theta written here. And we look for 2. So reading from the right, we look for 2. Well, we have a 2 here, and that gets mapped to 1. So what we write is 2 maps to 1. And then we go to the left composed function, and we find the 1, which is here, and the 1 gets mapped to 6. So we say 1 gets mapped to 6. Okay. Since 2 and 6 are not the same number, we have to go through a second pass. So going through again, we look for 6 now. So erasing what we had before, we look for 6 now in the right composed function. So we have a 6 here, and that gets mapped to 3. So in the second pass, we say 6 goes to 3. And then we go to the left, and we find the 3. So we say that 3 gets mapped to itself. So we say 3 gets mapped to 3. Although we have 3 going to 3, 6 is not equal to 3. So we still haven't closed the loop. So we have to go through a third time. This time we start with 3, because 3 is at the end. Just like we ended with 6, so we started with 6. So here, since we ended with 3, we start with 3. So we say we look for 3 here. Well, 3, erasing these old orange marks, 3 gets mapped to 6 here. So 3 gets mapped to 6. So we write 3 goes to 6. And then looking for 6, well, we can just see 6 gets mapped to 4. So we say that 6 goes to 4. But again, these two elements aren't equal to each other. So what we write is we go through a fourth pass now, pass 4, and we start again with 4, and that's because we ended with 4 here. So looking at 4, we find that 4 on the right function, 4 gets mapped to 5. So we write 4 goes to 5. And then what does 5 go to? 5 here goes to 2. So we write 5 goes to 2. And we've ended on 2. So we check, does 2 equal the number we started with? Well, it does, because we started here with 2. So now the loop is closed. And the way that we read off the elements of this loop is we read off the first number that we started with in each pass. So we erase this too. So we read it backwards again. So we say the cycle is 4, 3, 6, 2. So the cycle here, so we can then say that psi, composed with theta, has as one of its components 4, 3, 6, 2. And that's because we read all of the first elements of each pass, we read it backwards. So 4, 3, 6, 2. And because 3, 6, and 4 are all in this cycle here, we don't have to consider them when doing passes through psi composed with theta. Because let's say we started with 6, right? We already know that we have a cycle that takes 6 to 3, 3 to 4, and 4 to 2. So we just don't have to consider 6 because it's already a part of this cycle. And what we'll get out of it is just this same cycle again. So we only have to consider the numbers not in this cycle and not in the previous cycle. So the previous cycle had 1, and this has 2, 3, 4, and 6. So the only number remaining is 5. So let's consider 5. And again, I'll print out the previous, or what exactly we're looking at, just so I don't have to keep scrolling up. So we go through a first pass of this composition. So we say in pass 1, we look for 5. So 5 gets mapped to what? Well, here 5 gets mapped to 2. So we say 5 goes to 2. And then in the left function of the composition, we say 2 goes to what? Well, here 2 gets mapped to 5. So we go 5 to 2 and then 2 to 5. So just like 1, we've already closed the loop. So the loop is closed. Meaning psi composed with theta contains just 5. 5 gets left alone. So what we found is that this composition is equal to, well, it leaves 1 alone and it leaves 5 alone. So it's equal to 1, 5, and then this long cycle, which is 4, 3, 6, 2. And we should check whether or not this is equal to what we found before. So this is how you do it by directly multiplying them, or you can just compare by multiplying psi composed with theta on an arbitrary element. And what we found there was that it's equal to 1, 5 and the cycle 4, 3, 6, 2, which is exactly what we found. So this is just another way of writing out cycles, writing out permutations, so elements of Sn. And cycle notation here, after you get a hang of it, becomes an incredibly useful tool and will be used later on in group theory courses. So thank you for watching.